Chapter 8, Unit 2. Type 1 errors. A type 1 error occurs when a researcher rejects a null hypothesis that is actually true. So basically your answer ends up in the rejection regions when it really shouldn't have. In a typical research situation, a type 1 error means the researcher concludes that there is evidence for a treatment effect when in fact the treatment really did have no effect. It should have been in there with everybody else, no different from the mean. So here's an example. In the example of the waitresses wearing red shirts, suppose that researchers select 36 men who were already good tippers. So even if the red shirt or the treatment had no effect at all, these men will still leave higher than average tips. And the researcher is likely to conclude that the treatment does have an effect, when in fact really maybe it didn't, because these were really good tippers anyway. So type 1 error is not a careless mistake. The sample data really do appear to show a clear treatment effect. Type 1 errors lead to false reports in scientific literature. So the main reason and way to remember a type 1 error is it's like sending an innocent person to jail. It's kind of a bad thing. Let's talk about the probability of a type 1 error. The probability of committing a type 1 error is actually equal to the alpha level. So say that your alpha level is 5%. There's a 5% probability that one of these samples will occur. So alpha level determines the probability of obtaining a sample mean in the critical region when the null hypothesis is true. So when sample data are in the critical region, the appropriate decision for a hypothesis test is always to reject the null. And normally this is the correct decision. Occasionally, sample data are in the critical region by chance without any treatment effect. And if that happens, then the researcher would make a type 1 error. So anytime the null hypothesis is rejected, there's a chance of type 1 error. The researcher can select the risk of error they are comfortable with by choosing the appropriate alpha level. Selecting a small alpha level will minimize the probability of type 1 error. Let's look at type 2 errors. So a type 2 error occurs when a researcher fails to reject a null hypothesis that is in fact false. In a research situation, a type 2 error means that the hypothesis test has failed to detect a real treatment effect. So a type 2 error occurs when the sample mean is not in the critical region, even though the treatment really did have an effect. It doesn't show up in our sample data. So many times this happens when the effect of the treatment is relatively small. The treatment does not influence the sample, but the magnitude of the effect is not large enough to move the sample into the critical region. So the decision is to fail to reject the null. A type 2 error is not as serious as a type 1 error. If a researcher still believes results should be significant, then the researcher can actually repeat the study to try and demonstrate that the treatment really does work. It's impossible to determine a single exact probability for type 2 error. It depends on sample size and effect size. However, it's typically presented by beta, which is a Greek letter B. So think of type 2 error as letting a guilty person go free. It's not as bad as type 1 error. Remember, type 1 error is the same as sending an innocent person to jail. So type 1 is a much greater consequences. So let's look at possible outcomes of a statistical decision. A hypothesis test always has two possibilities for error. The first one is a type 1 error, which is called alpha, which is rejecting a true hypothesis. The sample data are extreme by chance and may give the appearance of a treatment effect even though there is no real effect. And the type 2 error, which is beta, which is failing to reject a false null hypothesis. The sample data are not in the critical region even though the treatment does have an effect on the sample. So here's a nice table that kind of shows you what the researcher's decision is as opposed to the actual situation. Let's talk about selecting an alpha level. So an alpha level helps determine boundaries for the critical region by defining the concept of very unlikely or extreme outcomes. An alpha level determines the probability of type 1 error. The primary concern when selecting the alpha level is to minimize type 1 error. By convention, the largest permissible value is alpha equal 0.05. With no treatment effect, alpha of 0.05 means that there's a 5% risk or a 1 out of 20 probability of rejecting the null when it's actually true and committing a type 1 error. Some researchers and certain fields use a more conservative alpha level, such as 0.01 or 0.001, to reduce the risk that a false report is published. For example, if you were developing a new medical drug and you were concerned with it being not within the certain parameters, maybe you were going to kill somebody if it wasn't. You might use an alpha level of 0.001 or even 0.0001 to make sure that your drug is exactly the way it's supposed to be. A lower alpha level also means that the hypothesis test demands more evidence for a treatment to be significant and have an effect. So there is a trade-off, especially in educational research. So, for example, an alpha of 0.00001, 1 in a million, would mean almost no risk of type 1 error, but the critical regions would be so extreme that it would be impossible to ever reject the null. So researchers try to balance the risk of type 1 error with the demands of the hypothesis test. And again, the most common alpha levels, especially in education that we use, are 0.05 or 0.01, and then other fields also use 0.001. Education typically uses 0.05. Medical research might use, again, like we talked about, 0.001 or 0.0001. So here's the location of the critical region boundaries for different alpha levels. And remember, you can always look these two-tailed tests up in your tables. Alpha level 0.05, you would split it in half. That would mean p-value of 0.0250 in each tail. You'd look it up in the tables and you'd find a z-score equal to plus and minus 1.96. You could do the same thing for alpha 0.01, the same thing for alpha 0.001. So you can always look these values up. Some people choose to memorize these three since they're most common, especially the first two, 0.05 and 0.01. They just don't want to look them up for every problem, so you could do it either way. The learning check problem 1. What does a type 2 error mean? Well, it actually means that the researcher has falsely concluded that a treatment has no effect. Learning check problem 2. What does a type 1 error mean? Well, it means that the researcher has concluded that a treatment has an effect, when really it does not have an effect. Learning check problem 3. What's the consequence of increasing the alpha level, for example, from 0.01 to 0.05? It will increase the likelihood of rejecting the null because your boundaries and the tails will be increased, and it will also increase the type 1 error.